Okay, so when you go ahead and look at most periodic tables, you see that the mass number listed on that periodic table is not a whole number. Instead, it's going to be a number that has a decimal component to it. That is because periodic tables don't list the mass number in most cases. Instead, they're going to list something called the atomic mass. So just say the mass values as I said on the periodic table. Okay, so when you go ahead and look at most periodic tables, you're going to notice something a little bit different about them from the ones that I've used so far in class. And that is that most periodic tables have decimal components to the numbers. That is because periodic tables, in most cases, use the atomic mass of the element rather than the mass number. Remember, mass number is the number of protons plus neutrons. The atomic number is a little bit different because it takes the isotopes into account. So the atomic mass is actually a weighted average of all the different isotopes of that element. So how we go ahead and calculate that is we take the abundance of the first isotope times the mass of that isotope. And then we're going to go ahead and add to that the abundance of the second isotope times its mass, and we keep doing that for all the isotopes in our sample. So if I look at an example of hydrogen, remember I have 3 different isotopes in hydrogen. I have hydrogen itself, deuterium, and tritium. All of them have 1 proton, but they have different number of neutrons, which gives them different mass numbers. So the traditional hydrogen with 1 proton is the most common and has a very large abundance. Deuterium, which has 1 proton and 1 neutron, has a very small abundance, but still measurable. And then tritium, which has 1 proton and 2 neutrons, is very rare. So it does exist, but it's really close to 0% abundance. So for that, we don't even include it in this calculation. So for my atomic mass of hydrogen, I'm going to take my abundance of my first isotope, which is hydrogen itself, times its mass. And I'm going to add to that the abundance of my second isotope, which is deuterium, times its mass, which is 2. So when I go ahead and do that, I get the 1.001, which is much closer to what you see on most periodic tables. So let's go ahead and do this calculation for some examples here. So the first one I have is chlorine. So I have 2 different isotopes, isotope 35 and 37, and they have different abundances. So I'm going to plug this into my calculator. I'm going to take 0.7578, which is the abundance of the first isotope, times its mass. And I'm going to add to that the abundance of the second isotope times its mass. I'm going to go ahead and plug that in. I get the value of 35.48. Which should seem like a reasonable value when we look at our data. So I have 2 different isotopes, but I see that the isotope number 35 is much more common. It's about 3 times as common as isotope 37. So my mass is closer to the mass of my more common isotope, which makes sense. So for boron, I again have 2 different isotopes. This one I have isotope with a mass of 10, and then boron 11. So if I look at this one, I want to take a second, kind of make a mental prediction. If I look at the abundances, I see that isotope 11 mass is much more common. So I think my atomic mass is going to be closer to 11 than it is to 10. So let's go ahead and plug it into our calculator. So we take 10 times its abundance, 0.199, plus 11 times its abundance, 0.801. So then go ahead and plug that in my calculator. I get 10.80. So if we were to think about rounding this number is much closer to 11. It'd round up to 11 versus 10 as a whole number. So that makes sense with our data. So I hope this helps explain where some of those decimal values come from on the periodic table. We can still use the periodic table to help us find things like protons and neutrons. It's just we need to keep in mind that sometimes we need to do a little bit of extra work to understand where those values come from. So if you have any questions on this, please let me know. Otherwise, good luck and thanks for watching, everyone. Bye.